must tell you right from the start that it's a little bit out of my comfort zone because I'm not used to speak to an audience which is not in my field, so it was a challenge for me. So I'm a research engineer in Thales Research and Technology, which is one of the 5 corporate research centers of Thales. Thales is a French group, I don't know if all of you know it, specialized in secure and defense systems for a wide area, for wide domains. So we have aerospace, space, transportation, communication systems, underwater systems, and so on. And I specialize actually in algorithms, mainly data-driven artificial intelligence. For the past years, I was working on data science problems, and I'm interested in machine learning and stuff like that. So. This talk is called The Landscape of Deep Learning, a quick overview. Well, actually, when I started preparing for it, I had in mind this blooming field, okay, no pun intended, where I was going to pick up each and every flower and then describe it in a thorough way, and then by the end we would have a very nice bouquet of every different flavors. And somehow when I prepared it, kind of slipped out of my hands and has a life of its own. So I kept taking a step back from the field and a step back and a step back, and now I'm standing on top of a mountain actually. And so I warn you from the beginning not to be disappointed. I won't be getting into the particular flavor and perfume of each flower. We are going to have a view from the top, and hopefully the messages you will get are the key concepts, and so not so much the hows, but the what and the whys, let's say. Okay. So first of all, deep learning is a term which is not so new. We only heard about it. In the past decade or so. But actually, it's a term existing ever since 1986, and it was introduced by Rina Dechter in the machine learning and community, and it was. She was more on the let's say old-fashioned AI. Now it's called old-fashioned AI, the automated reasoning and stuff like that. And then it was adopted with respect to artificial neural networks by Eisenberg in around 2000, and it's been widely used with respect to neural networks with many hidden layers only since 2006 or so. And I'm going to be unjust to a lot of researchers actually, because I'm only citing the 3 Benjo, Hinton, and Lecan, who are the kind of the both the pioneers in a way of deep learning field, but also the main. So in French we say this porte-parole, so the main speakers for this technology, the guys who really put it out there for the world to see. So there are many researchers involved in deep learning throughout the years. Now, if we go a little bit deeper into this concept, deep learning, well, it's towards deep and learning, and actually the key concept here is learning, and this will be the drive of my talk. And the deep part is what makes it work nowadays, and this is why we. This is a reason for their revival. So when we say learning, we don't mean any kind of learning. Learning can take a lot of different shapes in us humans. We talk about machine learning, and this is a term which was coined in 1959 or so, in the 60s. And there was this formal definition, which is very nice, by Mitchell. And it goes like this. Learning means a computer program learns from experience with respect to some class of task, T, and a performance measure, P, if its performance at tasks in T, as measured by P, improves with experience. So, a key concept here is learn from experience. And this kind of induces a notion which is there is kind of statistics going on. Experience means we accumulate stuff and then we do something with it. So the key word here is statistical. And actually, it's a contraption. When we say machine learning, we usually say statistical machine learning. So all throughout the talk from now on, I will just say machine learning when I refer to this. And statistical machine learning then means that it's based on data. The experience that the previous definition talked about is formed of examples, and you have here a most famous classification problem for iris data for flowers. And this kind of data we are talking about, but data can take many other shapes. It can be also sound, it can be text, it can be graphs even, it can be knowledge representations, it can be programs, it can be a lot of stuff. Data takes, well, it's a new goal actually today, and it takes a lot of shapes. And so statistics on this data means we are going to be using statistical tools, and we are going to be interested in algorithms to make predictions, to estimate complicated functions from random observations, and we will do this to automate decision making. And actually, this is one of the many goals of artificial intelligence. So what are the other goals? Well, so a lot of disclaimers. I took a lot of this material from Wikipedia, from Scholarpedia, from everywhere on the net, actually. So this is perhaps not the consensus, so just bear with me. A lot of the stuff that I'm going to be saying are going to be overly simplified, perhaps. But as listed by Wikipedia, the goals of artificial intelligence are perception, reasoning, knowledge representation, automated planning, automated scheduling, natural language processing, and learning comes somewhere in this. And there are let's say two schools of thoughts, actually, when we talk about artificial intelligence. And of course, today, when we say artificial intelligence, everybody thinks about Google DeepMind and Facebook, facial recognition, and so on and so forth. But artificial intelligence is as old as computer science, actually. And in the beginning, and even today, the school keeps going, even though the data-driven one is in the spotlight. The second part is the symbolic AI. What do I mean by symbolic AI? We are going just to do a small digression about this, because what I want to point out is that the two fields are actually interrelated, and they will be for a long time. And if we want to really solve artificial intelligence problems better, we kind of need to know both. Okay, so and it's again an overly simplified. So I'm very sorry if there are symbolic artificial intelligence guys in the room. It's really. I'm taking an example to make my point and to kind of motivate why we need data-driven. So it's kind of a biased explanation of what symbolic AI is. As I view it, it's a top-down approach. Why is it a top-down? Because we start with the world and we try to model it in a deterministic and rule-based, based on expert knowledge manner. And this expert knowledge is explicitly captured in the shape of rules, which are predicates. So actually, this half field of artificial intelligence mainly uses logics and operations that combine together in order to do reasoning. So to infer something based on the rules, and then from reasoning, we can go to making decisions, and after making decisions, we can take actions. And once we took actions, we can even go a further step ahead and do planning. So let's take a very sketch example. So if we would be presented with this capturing of the world, which is this cute picture, what would the human do? Well, would reason about this, and this is just really an oversimplification of reasoning, we would just think about what are we seeing, what is this? And we would do something in our head, and we recognize that this is a cat. That would be a decision. I recognize that this is a cat, and then I will take an action. I will smile because it's a cute cat. And we can also do some planning after this and check out similar pictures on YouTube and such, and we would be very happy. Now, if we want to do this automatically in this, let's say, good old-fashioned AI, symbolic AI today, we would want to know what defines a cat, and we would need expert knowledge to define the set of rules that, that makes up a cat. And we would do a reasoning like this, okay, it's very loose logic, right? We would need to make up rules like if fur and color in some set of colors and ears in some set of ears, because, okay, we need to take into account all situations, very sorry for that, and eyes and nose and mouth and mustaches and paws, and this could go on and on and on, and several thousands of rules later, this kind of automated rule-based, experience-based system would go then cat. Okay, sorry, I'm speaking too loud. Is it okay for you? Also, I forgot to say that feel free to interrupt at any time, because it was really difficult to set up the right granularity for this task. So, if we need to capture this experience, we need to make up all the rules, and we will always find some examples like this one who don't play really by the rules, because in real life there are a lot of unknown and uncertain factors. Okay, to be fair with symbolic AI, because I'm not in the not symbolic AI camp, it's really an overly simplified example, because there is symbolic AI reasoning under uncertainty, and we can do fuzzy logic, and we can do a lot of stuff which kind of get closer to the data-driven approach, but this is just to make a point. Now, if we would go even further, and we take our initial set of rules, we would need to really define automatically the predicates in my rules, like fur, ears, and this would incur another set of rules, like it becomes really a very complicated problem, knowing that in order to find the rules, a good rule is a non-ambiguous rule, but in the same time, it's generic, it needs to describe all cases, and yet it needs to be discriminative enough so as to separate the classes and so on and so forth. And some problems, as I hope I showed with these examples, are really complex to model, and are one of the motivations for which today data-driven artificial AI takes the stand and make computers solve different kind. Let's say we can tag them like perception, in a way, tasks that are difficult to do with an expert-based system. So in the real world, this kind of stuff like textures, images, sound are high-dimensional functions, which are very hard to describe analytically. It requires a lot of expertise, and sometimes it's even impossible. And I'm speaking very fast. And so we need to approximate them, to estimate, to predict, and usually we will take iterative approaches. And now I'm closing this parenthesis, because it enters the field of data-driven AI. So instead of doing this, we let the model refine itself progressively from examples. And I put there and hope for the best, because when we step into this side of the world, the problem is no longer controllable in the same sense as before, because well, we don't make up the rules. We let the rules emerge from themselves. And actually, as I said before, symbolic AI works in many other cases, and in general, we need a mixture of both in order to really go towards very efficient automated decision systems. Now, data-driven AI. So this talk is about data-driven AI. I see it as a bottom-up approach. Okay. So instead of starting with what is the model, we start with the examples like the humans do. And at this point, I need to really highlight another thing which is lacking in my speech. is that I'm not going to talk at all, I'm sorry about that, about biological inspiration. I'm really convinced that there is something to do there, and it's a fascinating topic. I had to make choices, and so I will only give the algorithmic view of this, knowing that there are a lot of other things to research and also about the implementation as well. So, data-driven AI, so instead of explicit rules, increase the knowledge by accumulating examples. And the model emerges from them, and it's a trial and error process. And then we can do what's called inference. Okay, it's a little bit of double meaning, because inference also exists in the logic part, but in the data-driven AI we also call inference this kind of operations where we take an example and we put it into the machine, and this complex or not so complex machinery takes place, and then the output of the model goes cat. And the next step is we would take an example like this one, and which it never saw before in its experience, and then it would also be able to infer and say that hopefully this is a cat. I'm not sure the machine would agree with me, because as you can see, drawing is not my main skill. But okay, so this is data-driven AI in a nutshell. And after this very long introduction, the agenda of this talk. So we are going to address some more machine learning basics in the following. How am I doing for time? And then we are going to address a class of machine learning, statistical machine learning techniques, which are artificial neural networks, because actually this is what the talk is about. And in artificial neural networks, now everybody talks about deep learning. Deep learning models are artificial neural networks, actually. And if we have time, I will also talk about some final considerations from an industrial point of view. Now, machine learning. Some tasks of machine learning which define actually the needs for methods of this field. One task is clustering. Okay, the order is not necessarily the logical one, but well, it's just to give you an overview of some of the very important tasks to be solved with this kind of approaches. So clustering, what is clustering about? You have a set of points, and you want to separate them somehow. You want to find a property which puts a group of points together and another group of points together. And then you have another task which is called classification. In this case, the clusters have been previously formed, and you have a group of blue points and a group of reddish points. And then you get a new point, and you want to assign a class to one of these points. This is what we call classification. And then another machine learning task, which kind of overlaps also with statistics, is regression. Everybody knows it. So it's basically curve fitting, finding the model that underlies the points. And then you have some other interesting tasks that are nowadays is kind of a big loop ahead. Another task that is now successfully solved by machine learning techniques is this kind of task, like transcription. You get a picture or let's say another model like this one with the blue points, gray points, and the red triangle, and they have nowadays automated systems that do the description of this picture, like blue and gray circles and one big red triangle on a canvas. So this is also a nice task which is solved with machine learning today. And another task, it's really a subset of all the tasks that we can do, which is important. I put that up there because for industry problems like ours in Thales, this is an important one. Anomaly detection, it's a little bit different than clustering, because in clustering you have this underlying hypothesis that you have like the same amount of points in the cluster, so we don't really aim for clusters of 1 point. We aim for examples which span the space of possible configurations. And in anomaly detection, there's a lot of normal data, which makes like for one big cluster, and then some isolated points that we would want to detect. So the same techniques may not be needed to put in place for this kind of task. And the thing is that these are rare events for which you don't have a lot of training data. So this is very important. Okay, training data comes after, but there are many more tasks that are performed today with machine learning, like machine translation. Nowadays, automated translation is a huge success. Everybody is using Google Translate, and a couple of years ago, we would have really a big laugh, and I still get laughs in like languages which are a little bit rare, like Romanian. When I translate it from French or from English, it always does funny things in translation. But for the main languages, the ones that are spoken by a lot of people and for which a lot of examples present over the time, the machine translation gets really, really good. And then you have density estimation, interpolation, missing values. These are also very important problem for industrial cases, but also generating new examples, so synthesis, and a lot of nice thing as denoising, also important for industry, but also, well, the industry with the machines, but also the industry for the entertainment and stuff like that, because you can do nice movies and stuff like that. Okay. From the algorithmic point of view, the needs of machine learning, basically, I'm not talking about all the needs, but the ones that we need to make machine learning algorithms work. So basically the data, actually. It all starts with the data, and every data science problem is like that. And we need balanced data sets which capture the diversity of the subsequent space, because we use these examples to infer, to predict outcomes. So the outcomes need to be in the class of the examples, otherwise we will get really a bad performance. So for instance, in binary classification, we would need a comparable number of positive and negative examples. In phase classification, we would need all, let's say, some characteristics which are represented in order to get, let's say, fair generalization and not induce bias in the data set. We also need to have statistical significance, the adequate number of available samples in order to predict something. And we need to have diverse data sets capturing a lot of already physical properties like different angles, views, occlusion, deformation, contrast, clutter, a lot of stuff. And these are the things because the result of the algorithm is really dependent of the quality of the inputs. So if you have crappy inputs, you will have crappy outputs. And in machine learning, one of the needs also for machine learning then, which now steps into the application of the algorithms, you need strategies to avoid underfitting or overfitting. Underfitting meaning that you don't capture well the model. For instance, using a linear model for a non-linear signal, this would be an underfitting problem. And overfitting means that you learn actually all the small variation, all the noise in the signal, and then you are not able to generalize at all when seeing something which is out of this. Well, you will just learn the noise actually. And now we go to the approaches of machine learning. So machine learning problem is a two-stage process. This is very important. And it consists of a training phase where we accumulate all the data and actually the model emerges. And then a test phase. And there are a lot of confusions about the terminology. I'm using test set for I'm usually using test set, but some people also call them validation. I will explain what I mean by validation set. So these two sets of data is very important. They need to be distinct because we don't want to test the model on the data that it learned from. We want to test its generalization power. So we want to test an example which is out of the data set. And the goal is to minimize some error, some metric on each of these sets. And sometimes this may fail, and strategies need to be put in place in order to get good generalization while getting a good training performance. And there are two major ways of learning. I'm just putting them into two broad categories, supervised and unsupervised learning, knowing that you will have the talk right after on reinforcement learning, which is in between the two, so I'm not going to explain this. And supervised learning, in which tasks like classification and regression fall into, they involve ground truth. So instead, not only having the data, but also having the knowledge about what this data is about, labels of the data set. And so this would mean class labels, reference signal. And the idea in this kind of methods is to minimize, again, a metric or an error between the obtained output and the expected one, the label. And the other kind, the unsupervised learning, in which the clustering-like tasks fall, there is no ground truth available, and the structure emerges by setting metrics on the data. For instance, we need to set some distances between the points. I'm always putting quotes because I'm saying distance, but I not always mean Euclidean distance. And the goal would be to have the smallest intra-cluster distance, so the points which are the most alike are put together, and the largest intra-cluster distance of the point must be separated the best. Okay? And just like a stochastic list of methods, because there are a lot out there. I'm just putting some to give you keywords, actually. I'm not going to explain them. And there are a lot of overlaps. So for supervised learning, well, one of the most famous ones are supervector machines, and these caused the fall of neural networks for a lot of decades, actually. These and other factors. And in unsupervised learning, you have also some methods like k-means, which is the most used industrially to date, but also density-based clustering, where other kinds of distances are and probabilities are used for clustering, and expectation maximization also on the probabilistic setting, and artificial neural networks, which are in both. So actually it's kind of unfair because a lot of methods are used for more than one class of, well, so as I said, the world is not a binary partitioning, okay? There is a lot of gray areas. But artificial neural networks are there, and what's nice about them, what convinced me to look into them a couple of years ago, is that they kind of seem to be generic enough to handle all these kind of problems, provided that you change and tweak the models as you need. And solve problems, underlying problems, to build them in an efficient way. So now we arrive to the next part of the talk, which are artificial neural networks. And again, I apologize. I'm only considering what I would call basic neural models, where practically no biological inspiration, or very little, is at stake there, besides from the terminology, so neurons and synapses, which are connections between the neurons. And I'm very much aware that you will have talks about spiking models, which are more biologically plausible. So the way that the neuron activates is, well, what they call the third generation neural networks. I'm not going to talk about that at all, although I think it's fascinating. So we are just going to stick to basic artificial neural networks which work today. So before going to what's an artificial neural network, we need to understand what's an artificial neuron, because an artificial neural network is a network of neurons. So how does an artificial neuron work? It gets some input vector x. It has what's called an activation function f. And the inputs are connected to this neuron with different strengths. which are strengths, which are captured by the weights W in my model. And then the output of the neuron would be the inner product, the combination of the inputs and their strength pass through the activation function. And there are many examples of activation functions that I put here. And one of the most used today in deep learning methods, contrary to the intuition, because they do a lot of derivations in deep learning, and this is kind of counterintuitive, is the rectified linear unit, which is a function going max over 0 and x. So, and this is the one which actually is responsible for a lot of success today in deep learning methods. So now, a network of artificial neurons is simply putting together all these networks in the simplest feed-forward structure. Everybody is connected to everybody. You have an input layer which connects to hidden layers, where we call them hidden because we don't see the outputs at the end, and an output layer. And the output would be like a composition of functions throughout the different layers. The n being the last layer, and then you have, so you kind of compose actions of neurons throughout the layers. Now, how to make this network learn? So the most famous method of all, which is not didn't start in 2006, obviously, it started well in the 80s, is backpropagation, error gradient backpropagation. So the goal would be to approximate some function f star of x by so to approximate some function f star of x by a function f of x, which is a function output by the neural network. For instance, in the classification example, at each point x, the network would output a value y hat, which is close to y, and the goal would be to find this y hat, for this y hat, the parameters bringing f the closest to f star. So this is the goal. And what is how does it work? One needs to minimize a non-convex. Usually the combination of these functions becomes non-convex. It's a complicated optimization problem. And one needs to minimize this non-convex loss cost function. And the way to do it is, well, in two stages, actually, in this deep feed-forward, not deep, but feed-forward network, you do a forward propagation, meaning you compute the loss function, and then backpropagation amounts to the chain rule of derivatives computation, actually. And this is in scalar setting, and when you go into multidimensional setting, you would have then the Jacobian gradient product from layer to layer that you propagate backwards. And the gradient that you propagate is the error, the loss between what the output that you get and the expected output that you would want to get. Okay, so I think that I said it all. There are some things to consider when doing this. So this function to be approximated is a non-convex function, and it has, well, in my example, it has a global minimum, and this gradient descent, actually all the methods, most of the methods, not all, but most of the methods in deep learning are based on gradient descent, and it can be stuck in local minima, and in so in this setting, sometimes you can be stuck in a bad local minimum, but most of the time deep learning methods go towards good local minimum. So actually it would be an approximation of the global minimum, which would be enough to get the right performance of your method. Some things to be said here: when you do gradient descent, you really need to be careful of the learning rate. The learning rate is what the pace on which you change your gradient values. If it's too slow, then you can have slow convergence. If it's too high, you possibly we can get no convergence because it can move you move along the steepest descent and you can go out of your graph, and you have problems like if the slope is too small, then you will have the problem of vanishing gradients. The gradients become progressively close to zero. If you have cliffs, like very high steeps, then you can have exploding gradients and then lose convergence. And in order to solve these kind of problems, most methods introduce some kind of regularization on the parameters, on the learning rate, and so on and so forth. Now, a little bit of history. I didn't do a lot of usual stuff like a biological neuron, the whole history of neural networks, but just for the sake of completeness. So the first occurrences were in the 40s, and then you have a lot of kind of key models that made these technologies work. So like the perceptron, then the neocognitron, and Yann-LeCun's convolutional neural networks with backpropagation in the 90s, in the end of the 80s, and then successes for speech with multi-layer perceptrons, and well, the famous convolutional neural network LeNet 5 in the 1980s, and then you have some other models of neural networks that I didn't put here, but I gave a thorough list of references that will lead you to all the history of neural networks throughout the time. So what happened? Why didn't all these models that in that period emerged like mushrooms after the rain? Well, one of the things is for instance for the multi-layer perceptron was the famous XOR problem, where this is a linear model and we have a nonlinear space, the XOR, where the opposites, we can't partition this space. We can't cluster this with a linear model. And then there was also the universal approximation theorem, which kind of put the brakes on deep learning, on many hidden layer artificial neural networks. And this universal approximation theorem stated that one layer wide enough is enough to approximate with any precision any kind of function. And this was a problem because they didn't say how wide, and it was unpractical to, well, actually it's exponential. If your function is complex, it's exponential to approximate it, and then you would need very, very, very wide networks, and the computing power simply wasn't there, and sometimes also you have convergence problems. So also support vector machines, which I mentioned before, were doing better and with simpler methods. And so this was kind of the brakes for neural networks. But then something happened in 2006 or so, and we arrived to the era of deep learning models. Okay. So what happened is that these researchers that I cited before, they found a way to pre-train each layer, so really accelerate and enhance the power of the learning method by doing unsupervised learning of representation, of inside features of the network. And this led to all these kind of great stories, like the ImageNet classification challenge that was solved with very nice precision in around 2012. And the precision was like 30% accuracy at that time, and it went to, now it's 0.5 or something accuracy. So it's really solving this task of object recognition for computer vision. And then you have machine translation, as I said before, and the recent one from Google, the Google Neural Machine Translation System, really takes this translation a step further and leads to a result which is quite close to what an expert human would give for the same translation. And then some very exciting well, progress in health were made with deep learning. So nowadays everybody wants to use it, and of course AlphaGo, which is really the success that made everybody talk about deep learning, which is a combination of reinforcement learning and deep learning actually. So what's new? Well, the depth for once. We have now deep learning methods suppose that the number of hidden layers is bigger than 2. Okay, so as much as 3 layers is already deep learning, but nowadays the successful methods, for instance in image classification, have hundreds of hidden layers. Why is that? Because it based on it encompasses an assumption that complex concepts are hierarchical composition of simpler concepts. And this is what us humans do. We decompose a problem into simpler problems in order to solve it. And also what's new, okay, this was not a new algorithm, obviously, stochastic gradient descent, but this, its application in deep learning became pervasive and actually kind of accelerates a lot the optimization and solves the problem much easier. And then you have meta algorithms which are involving what we call the hyperparameters of the network, the hyperparameters being all the topology of the network, the width, so the number of neurons per layer, the number of layers, the activation functions, but also the learning rate and so on and so forth. And you have algorithms like ADAM or ADAGRAD or RMS-prop, which is one of the most famous for adaptive learning rate optimization. And then you have a very nice thing which is called batch normalization, which actually, in a sense, stationarizes the learning process by doing a Z normalization of the activations, so meaning that we subtract the mean of the activations and we divide by the standard deviation. And then when distributing all these calculations, because deep neural networks become very computationally intensive, when distributing this onto different machines, we won't get mismatch of the results because of the statistics of the local computations involved. And then some other nice techniques which really make up for the success of deep learning are dropout, which consists in highly accelerating and also robustifying the learning process by randomly drop units during training. And this prevents the overfit, prevents the network to, prevents the neurons to kind of conspire together and learn only the training set and not being able to generalize. So as I said, deep learning can be made to work by tuning the hyperparameters. And this can be done manually. It requires some skill. And also automatically, you have like random search method and you have grid space methods, so in order to consider all the parameters and find the optimal configuration. And how do we know if we got the optimal configuration? Well, we need to test several configurations, and this is when a third set of data comes in scene, the validation set. And this validation set is there to set up the right configuration of the hyperparameters, and actually is there to to kind of stop the earliest configuration on which the error on the validation set is lowest, and then when the error on the validation set goes up, then it means that we would be overfitting. The generalization of the network would be bad. So this additional data set kind of is used in order to to prevent overfitting, let's say. And then also one needs to choose the appropriate performance metric For instance, accuracy is nice, is what usually people say, okay, the percentage of accurate classification, but in many problems, this is not the right metric to use, for instance, in image classification, because false positives or false negatives don't have the same impact. If you are checking for cancer, you wouldn't want to miss one. So then a better metric would be the receiver operating characteristic, for instance, where not equal importance is given to the false positives and false negatives, or the true detection and the false detections. And also, I won't have time to go onto this, but deep learning highly relies on regularization techniques, a lot of regularization techniques actually. So in a nutshell, deep learning is about optimization, but is different from the optimization field, because the goal is not to optimize the objective function. The goal is to optimize a cost function in order to get the optimal performance on the performance metric that you set beforehand. So I still have like 15 minutes, 10 minutes, yes. Something like that?
Yes, 15 minutes.
Do you have questions so far? Should I go on then? Okay. So only a scratch of the surface of some of the deep learning models. So the most famous one, the one that, well, one of the most famous actually, but it's because it's about images that it's that famous, because it's easy for us humans, which rely so much on the eyes, to want to do tasks involving images. So this is what really works at human performance today, convolutional neural networks. I need to explain first what is a convolution, and what is different in convolutional neural networks with respect to the classical multi-layer fully connected networks I was talking about before. So convolution is basically a filtering operation where you take what's called a kernel, a convolutional kernel, so a signal, well, a filter, actually a filter that you pass onto your image, and you modify the values at each step with this filter in order to get some result. Classic examples of filtering, which are very powerful filters, for instance, in image, are this kind of filters, the gradients, which are, well, it's a gradient actually, it's a difference between two samples with as little as a difference between two adjacent samples. You can get a contour, an edge detection algorithm, which is very powerful, and this is what convolutional neural networks exploit. They exploit the fact that features in images are local. They exploit the fact that they exploit the translation invariance. If I move by 1 pixel, I still am the same. So they put these filters throughout the image, and they compute basic features, and they aggregate these basic features into more complex features, and so on and so forth, until getting a very abstract representation of the information that is in the image. And it's kind of, in a sense, it's kind of information compression, going to the quintessence of what's important in an image. So one catch of this, well, not catch, but a nice thing is that now, instead of having everybody connected to everybody, these networks have much sparser connections, so it's easier to implement them, and it benefits from the locality. It exploits the spatial locality, actually. And the key idea is that instead of manually designing the filters to go over what kind of combination of edges I should put together in order to have a complex shape, they kind of learn this combination of abstractions throughout the hidden layers of the network. And this is highly inspired, and this is the most biologically inspired that I'm going to get from the visual system, which has this 10 layers of different abstractions, and it goes from very simple contour detection and motion detection to a complex shape, a complex pattern of a cat or something, a concept of the cat. So the basic architecture involves 3 types of, I call them processing. So they are composed of these convolution layers, which have very few connections at the size of the kernel size, which can be a 3 by 3 or 5 by 5 kernel. It's a very small number of connections with respect to an image which has like millions of pixels to be connected otherwise. And so this is the first layer which extracts these basic features, and then this is passed through the activation function, which usually is the max 0x function, the rectify linear unit. And then, sorry about that. And then the second operation is a pooling operation, where it's basically a subsampling operation when statistics of the neighboring outputs are summarizing into one representative concept. And it also goes towards sparsifying the connections. And at the very end, for classification, there is a dense layer where you get the decision about which class you are detecting. Okay. And a key concept in this architecture is weight sharing, the fact that actually filters are going to be the same for a lot of concepts. An edge, an oblique edge, like a Gobber filter, it's the same in a cat, in a car, in a lot of concepts. So the weights can be shared throughout the layers. Now, a second type of networks are recurrent networks, which are kind of not an extension, but a complement to convolutional neural networks, where you exploit the temporality of the signal. So these are very good for time series, for text, for speech, where one, instead of learning the local dependencies, the spatiality of as in the image, they learn the temporal sequence. And one could do this with convolutions across the 1D signal, but then it would be a shallow architecture, and it wouldn't be able to capture very long time dependencies. And recurrent networks, well, they introduce time, so they introduce loops actually in the outputs. The current output depends on the previous output, so it's no longer a feed-forward network. And in order to learn in these networks, it needs to be unfolded, and then you do gradient propagation through time in order to learn this kind of net. So it works with backprop, but through time. And then it's going to go faster and faster, because these models are also more complex to explain. We reach more onto the first one were supervised learning mainly. Now we reach more to unsupervised learning, and we're going to, so we talk about autoencoders, variational autoencoders. So these methods, for instance, autoencoders are like two-part networks, which have an encoder part, a decoder part, and the decoder aims to reconstruct the expected input. And initially they were used for feature learning, so in order to engineering the feature, learn the features, and also for dimension reduction, because it's like from the encoder-decoder scheme, it kind of compresses the signal. And now they are a lot used for generative models, so for dataset augmentation. What I said before about data being important to capture all the variations, when we don't have this data, there are techniques to circumvent this problem, and one of the techniques is data set augmentation, and these kind of methods are great at this today. For instance, they can interpolate through the space of human faces into faces that they have never seen, and the human would really don't know that it's not really a human face. So in this way, the data set becomes more representative of its space, because we have more points. But again, one should be very careful, because biases can still occur, because if you only have glasses wearing people in your data set and then you do data augmentation, you will get glasses wearing examples as well. So, okay, so these are trained by mini-batch gradient descent, but also there are other techniques like recirculation, which was invented by Hinton, to train this kind of methods. I really need to step up. And then we have graphical models, which are the other main class of neural networks, where we use, hidden units are probabilistic, and they compute like a joint probability distribution of the internal states of the systems. And these are the Boltzmann machine, the deep belief nets, and these are all the things that Geoff Hinton does very, very well. And I will end here the part of about the models, and let you contemplate a little bit this, because this is the jungle of all the models that exist in neural networks. It's a little bit oversimplified for some parts, but it's very nice to see that there are a lot of models there with noisy input cells, with spiking hidden cells, with probabilistic cells, recurrent cells, and so on and so forth. And I'm reaching the end of my presentation with some final industrial consideration. When I say industrial, I'm talking about what would take to have deep learning methods in products like Thales has. Thales is into safety critical systems, so it's not about tagging the face on Facebook. This is not the problems we tackle in Thales application. Well, in some of them, yes, but in most of them we don't. And so there are a lot of our systems are embedded. So when we say embedded, we mean constraints, energy constraints. So I'm preaching the choir here that we need efficient implementation of deep learning, both in the training phase, in the learning phase, if we want the system to be more adaptive and not just be stuck with whatever it has learned, and then not work on a new situation when the context changed a little bit, and then we will need to retrain, and then we would need perhaps another architecture or another chip. And in inference, actually, we need also good implementation for inferences on the chip, because even today, real-time performance is not reached for image classification, for instance, of very, very, very small targets on very, very, very large images. So, okay. And now we need to get it. We need to get the performance, so the functional performance, and in the energy envelope budget. So energy. This brings me to the second point. So the energy consumption, both at training and the inferences, and because nowadays deep learning methods train for days, and they spend millions of euros on the electricity bills, and this is not possible to do this in the embedded systems. And I'm really just scratching the surface here, but I'm sure you all are convinced about this. And then the resources, of course, of the planet and so on. And there are two other challenges which are more algorithmic challenges now, to have these methods into our products, which are the explicability of the decision, and this is one of the main, and the trust. These are the main problems for adopting deep learning methods in safety critical systems, because we need to rely on the decision, and the human needs to know why the decision has been made. And as us, we are not able to say what makes me think that a cat is a cat. I'm not able, as you saw in the beginning, it's very difficult for me to say what are the rules that my brain follows to decide that a cat is a cat. It's the same with deep learning methods. They kind of make their own concept, their own belief about what a cat is a cat, and if the human doesn't know what this belief is, then it's very difficult to take the word of the network for it. And the trust. So we need to know that the decision will always be the same and we cannot tamper with. So another thing that I just briefly mentioned is transfer learning, because this is very important for us. Well, transfer learning is about taking a model which learned on a case and applying it on a different case. And for instance, in image classification, our images are nothing alike ImageNet. So we need to take, well, what works today is take a model which has learned with good performance on ImageNet and then start from there to make it learn on our images, and then the performance go up. And there are very successful cases of one-shot learning with only one more example for a different class that it didn't see before, and even zero-shot learning. And it relies on the assumption that the hidden units finally will learn to represent causal factors explaining the data, and then when you get a new point, it will kind of reach this cause and effect chain. And then what's also very important is multimodal learning, combining text with images, for instance, in order to do like image fusion and enhance the performance of the learning algorithm. And a word about explainable AI versus trustable AI. So explainable AI techniques like this, so visualizing what was important for the network in order to take its decision, can bring the human closer to adopting this kind of methods, because then the human can easily see that, okay, this resembles a guitar, so okay, and this resembles a Labrador, so okay, I can trust its decision. And trustable AI is a very, very important problem, for instance, in cybersecurity, where it has been shown that with a smart engineered noise, in terms of gradient, actually, taking the signs of the gradient, which is basically imperceptible to the human eye, you can get 100% error, actually. So the panda gets classified as a gibbon. So this is a very complicated problem for us to handle when you are talking about missile detection and stuff like that. Okay. Okay, it's filmed. I probably shouldn't have said that. For defense, obviously. Okay, I'm making it worse. So let's go further. So one nice example of deep learning application, a side walk there, is style transfer. Yes, okay, and that's it actually. And well, these are my sources. Actually, there are meta references because all of them contain like thousands, everything there is to know about deep learning today. Thank you.